So we can start. Okay. So welcome everybody to the AJS seminar of today. Today we have with us Giuliano Klun, who is last year PhD student in Sissa and is working in under the supervision of Professor Fonda at the University of Trieste. And they will talk about on Dini derivatives of real functions.
Thank you to everybody. Good afternoon to everybody. And today I thank Emanuele and Maria. So today I will speak about my last article with Professor Fonda and Andrea Specci that is about Dini derivatives of real functions. So to start, let me recall the definition of Dini derivatives that are four quantities that can be real numbers or plus or minus infinity that are called the lower right, the upper right, the lower left, and the upper left Dini derivatives that are respectively the lim-inf and the lim-sup from the right and from the left of the difference quotient of f between the 2 points x plus h and x. So the main problem we are going to tackle today is the following. Let f to be a real valued function defined over an open interval I, and consider the following set. The set of points of I where the lower left derivative is strictly less than the upper right derivative. And we ask, how large can this set be? To answer this question, we have to recall the most important theorem about Dini derivative of real valued functions, that is the so-called Danjois-Saxiang theorem, that states that given a real valued function defined over an open interval I, except for a set of measure 0, at each point x of the domain, one of the following four alternatives holds. Or f has a finite derivative at that point, or the two opposite derivatives, the lower left and the upper right, are real and equal, and the other two are respectively plus and minus infinity, or the opposite situation holds, namely the other two derivatives are real and equal, and the first one, namely the upper right and the lower left, are respectively plus and minus infinity, or all the four derivatives are infinite and the upper ones are plus infinity and the lower ones are minus infinity. This theorem was originally proved by Danjois in 1915 for continuous functions. 1 year later, Young proved the same theorem for measurable function, and 8 years later, namely in 1924, Sachs proved this theorem for arbitrary real valued functions. More interestingly, in 1915, in the proof by Danjois, Danjois explicitly constructed a continuous function defined over an open interval, realizing each of the previous four conditions on a perfect set of positive Lebesgue measures. But in its proof, the set P is totally disconnected, and moreover, if I has a finite measure, then the measure of P has to be strictly less the measure of I. So to tackle this kind of problem, how this problem can arise. And there are two reasons to study the set VF we have defined before. And these are the main sources of inspiration that bring us to study this problem. One is a problem of differential equation, and namely the method of lower upper solution. let me recall a definition on the book of De Coster and Abeth, 2006, in which a continuous function alpha defined over an interval AB and taking equal values at the boundary of that interval is said to be a W21 lower solution for a second order periodic boundary value problem if its periodic extension on R is such that for any T0 in R, or the lower left derivative is less than the upper right derivative of alpha at that point, or there exists an open interval E0 such that T0 belongs to E0 and the function alpha is W21 function over E0, and moreover for almost every T in E0, the second derivative of alpha is greater or equal than f of t alpha of t. And here the main question is, can the first inequality for Dini derivative holds on all the points of the interval AB or on a subinterval? The answer, we are going to show that the answer is no. Moreover, some other result about Dini derivatives can be found in a work by Professor Fonda and me in 2019, when we deal with an extension of Poincaré-Bolle theorem, and we tackled the problem of studying Dini derivative of a continuous function, and we discover that Dini derivatives satisfy a Darboux-like theorem, namely the intermediate value problem for derivative. Also, Dini derivatives has this kind of property, and moreover, Dini derivative at a point depends on the value of Dini derivative in a neighborhood of that point, at least for continuous functions. Namely, we can say that the Dini derivative at the point is less or greater than the lim-inf or the lim-sup of other Dini derivative in a neighborhood of that point. So the main theorem, excluding existence result that we are going to show after today of this paper, is the following. If f from an interval I real valued is upper well behaved, namely for every compact interval containing in I, there is a point that realize the maximum of f over that interval J, then the set VF is totally disconnected. So more interestingly, clearly, if f is continuous by the Weierstrass theorem, the set VF has to be totally disconnected, because a continuous function is upper well behaved, because a continuous function realizes maximum and minimum over any compact interval. But more interestingly, an upper well-behaved function can be very pathological. Namely, for example, the Dirichlet function is upper well-behaved, but also functions that are non-measurable can be upper well-behaved. Let me give an idea of the proof of this theorem by a picture, because the proof is not very difficult. Consider the function f on the interval AB, and consider the infimum of f over the entire interval AB. Then, up to a subsequence, we have that there exists a sequence xk converge such that f of xk converge to the infimum, and up to a subsequence xk converge to some point of AB that we call x check. Now we want to prove that the function f has to be non-decreasing over the interval x check b. Suppose by contradiction now that there exist 2 points alpha and beta such that alpha and beta are greater than x check, alpha is less than beta, but f of alpha is greater than f of beta. In this hypothesis, we can find an n sufficiently big such that f of xn is less than f of alpha because f of xn converge to the infimum. So consider now the function f restricted to the interval xn beta. On that interval, by hypothesis, the function attains its maximum at some point that we call x hat. And f of x hat is the maximum of f over the interval xn beta. But here, the maximum cannot be internal, cannot be extremal. The maximum has to be internal because x hat cannot coincide with xn because f of alpha is greater than f of xn and f of x check is greater or equal than f of alpha. And the same reasoning holds for beta because f of x check is greater or equal than f of alpha that is greater than f of beta. So the maximum has to be internal. But in an internal point of maximum, Dini derivative has to satisfy the opposite inequality. So Dini derivative, the upper right Dini derivative is less or equal than the lower left. So the function f has to be non-decreasing over the interval x check b. Namely, it has to be derivable almost everywhere here. So the function f cannot, the interval ab cannot be entirely contained in Bf. And so Bf cannot contain any interval. So the set Vf is totally disconnected. And this completes the proof. So let me consider the case when I is all the real line. And suppose that Vf is all R. Namely, in every point, we have that the lower left derivative is less than the upper right derivative. And we ask the following question: can the function f be continuous at some point? Because we know that the function f cannot be continuous on any interval. But can the function f be continuous at some point? Quite surprisingly, the answer is yes. And the function f can be continuous at many points. And this theorem gives the main existence result of this paper. For any totally disconnected closed set A contained in R, there exists a function f for which Vf is all R and whose set of continuity points coincide with A. How to prove this theorem? To prove this theorem, we have to previously prove two lemmas that are the following. The first is this: let psi be a real valued function, non-negative and continuous, and define r of x to be a function that is 0, that is 1 if x is 0 or x is irrational, and it is 2 minus 1 over p if x is rational but not 0, and x in absolute value is p over q with p over q reduced to lowest term. So if we consider f of x to be psi of x times r of x, we have that the set of continuity point of f coincide with the set of zeros of psi, and moreover, if psi is non-zero, then the upper right derivative and the lower left derivative are respectively plus and minus infinity. And if psi is zero, then the upper right derivative and the lower left derivative of f are 2 times the respectively equal derivative of psi. How to prove this lemma? This lemma, let me give an idea of how the function r looks like. This is a graph that gives an idea. The function r is similar to Thomas' function, namely the function that is 0 over the irrational points, and it is 1 over q over rational points of the form p over q, and it is the Thomas function is continuous at irrational points and discontinuous at rational points. And it seems to be a reversed version of Thomas function and deformed because it's a specular image here. This is given by the fact that we does not consider 1 over q but minus 1 over p, and the minus gives the reverse image, and the 1 over p gives the deformation we see in this picture. More interestingly, r of x can be obtained by polynomial combination of Thomas function and Dirichlet function. So how to prove this theorem? Here the problem is that when x is rational, we have to assume that the function we are dealing with is reduced to lowest term, and this also when we approximate irrational numbers with rational numbers. So the tools that naturally arise to deal with this kind of problem is continued fractions. Let me give a briefly recall of the most important properties of continued fractions. Continued fractions are a way to represent real numbers as the decimal expansion is. The representation in continued fraction is unique for irrational numbers, and it is not unique for rational numbers, but there exist only 2 possible different representations of the same rational number. Namely, is the same with the decimal representation when we say that 1 can be written as in decimal notation as 1, 0 periodic or 0,9 periodic. Is the same, is 2 ways to represent 1, but it represents the same number. But more interestingly, for quadratic irrational, the representation in continued fraction is periodic, and if we construct the sequence of convergence of the continued fraction associated to an irrational number, but also to a rational number, but in this case, at some point, the representation, the sequence of convergence halts, namely, the even the even convergence truncating the continuous fraction after an even number of steps is an approximation for excess, and the odd convergence are approximation by defect. We will work now in the case x is positive and irrational and psi of x is non-zero. The case when x is negative is the same, but in this case, the role of xn plus and xn minus is reversed because the odd approximant in this case are approximate by excess and the even are approximate by defect. In this case, we can calculate the difference quotient of f with respect of the 2 points xn plus and x to obtain that this difference quotient tends to plus infinity if n tends to infinity. So the upper right Dini derivative is plus infinity. Analogous calculation holds for xn minus, and the lower left derivative in that case tends to minus infinity. If x is rational, this reasoning cannot hold because the sequence of approximate of convergence at some times stops. So for every x rational, we can construct two suitable sequences, xn plus and xn minus, of rational points that converge from the left and from the right to x, and repeat the above construction. The idea is here that if x is a over b, we consider a over b plus or minus 1 over 2b to the power n. This guarantees that this sequence converge from the left and from the right to x, and its numerator tends to plus infinity. The case x equals 0 can be treated very similarly. So we can consider now the case when psi is 0, and again x is positive, because the case x is negative is the same. So continuity of f at x is trivial because in this case the squeeze theorem gives the desired result because the function is bounded between 1 and 2 times psi. So we can find two sequences of irrational numbers, xn plus and minus, converging from the left and from the right to x, for which the associated difference quotients converge respectively to the upper right and the lower left derivative. And this gives the desired result. But if, and then by a diagonal process, we can find two sequences of rational numbers converging to x from the right and from the left, carefully choose between the right and the left approximant of xn minus and xn plus that are irrational, for which we make exactly the same reasoning as above, the case 1, and we obtain the same result, that also in these points, the upper right derivative is 2 times the upper right derivative of psi, and the same for the lower left derivative. So before proving the main lemma, we have to the main theorem, we have to prove another lemma, that is the following. Let A to be a totally disconnected closed set. Then there exists a non-negative continuous function sigma A from R to R, such that sigma A is differentiable over the complement of A for all x in A. The lower left derivative is minus infinity and the upper right derivative of sigma A is plus infinity, and sigma A of x is 0 if and only if x belongs to alpha. How this function looks like, and here is a a picture of a graph of the function, or in the case A is the Smith-Volterra Cantor. The function looks like a countable union, a countable gluing of semi-ellipses of suitable height. And here the main problem is to find the right height of, namely the right height of the vertical semi-axis of this semi-ellipses, because the choice here is crucial, because a too big height produce that the function is not continuous at some points, while a too small height have the effect that the function is derivable at some points. So this choice is crucial. And the idea, we have made a lot of trial and error process, and the right answer here is given by the an idea in the article by Denjois that I will go to explain briefly now. Suppose for the moment that A is bounded, and suppose that A is contained in the open interval 0, 1. Now, A is closed, so R minus A is a countable union of open intervals UN. Then two cases can occur here. If we request that this union is made of intervals that are internally disjoint, then the union can be finite or countable infinite. The case when the union is finite is very simple. Just take semi-ellipses of arbitrary height, of arbitrary vertical semi-axis, and define it over the interval UN, and we are okay. Suppose now that the union of the UN are the union of the UN is an infinite countable union of internally disjoint interval, and consider the interval 0, 1 closed. Suppose to consider U1, then U1 over U1 you construct a semi-ellipse with horizontal semi-axis equal to U1 and height equal to 1. Then remove U1 from the interval 0, 1. What remains is the union of two closed intervals disjoint. So U2 will belongs to one of these two intervals. Suppose that U2 belongs to the first closed interval considered. So over U2, you construct a semi-ellipse with horizontal semi-axis equals to U2 and vertical semi-axis to be equal to the square root of the measure of the closed interval containing U2. Now remove U2 and U1 from 0, 1. What remains is the union of three closed intervals, disjoint intervals, and U3 belongs to one of these three closed intervals. Suppose that U3, for example, belongs to the second closed interval. Then you construct over U3 another semi-ellipse with horizontal axis equal to U3 and height equal to the square root of the measure of the closed interval containing U3, and so on for every n. So in formulas, this is the result on every un. Then we can modify the function that we call sigma tilde a outside the closed interval of the form delta y minus delta containing a to make it C1 on the complements and equal to 1 outside 0, 1. Because in this case, it's very simple to modify the function at the boundary to make to deform the function a bit to make that this function has value 1 at the outside delta 1 minus delta. It is C1 on the complement of this interval, and we can also assume that outside 0, 1, because we have space between 0 and delta and 1 minus delta and 1, to adjust the function to make it C1 outside this interval and constant 1 with 0 derivative outside 0, 1. So if A is bounded, we can apply lemma 3 and obtain the requested function sigma A. Then we can multiply the resulting function by R and apply lemma 2. What is going on here seems to be very complicated, but it is very simple in what we have done, because where sigma A is not zero, then multiplication by R of X gives that Dini, the lower left Dini derivative is minus infinity and the upper right is plus infinity. Where sigma A is 0, then multiplication by R duplicate Dini derivative, but at that point, but by construction, we have that Dini derivative of sigma A are already minus infinity the lower left and plus infinity the upper right. And so we have obtained a function that has the required properties. If A is unbounded, we can find a diverging sequence of points not in A, and we repeat the above construction for every set AN that is AN intersected with XN, XN plus 1. Here, this set are closed and totally disconnected. So the previous theorem applies. And since Xn and Xn, the points Xn does not belong to A, they belongs to some UN. So you have space in this open set to deform a bit the function to make it C1 and with 0 derivative at the boundary of that interval. Then we can define C to be the gluing together of all these functions that guarantees derivability in the neighborhood of each xn because we are over an open interval. So gluing together all the functions sigma an gives the desired result. To conclude, I want to stress on 3 open problems that remains after this analysis. The first question is, if f defined over the interval I, real valued, is continuous or even upper well behaved, is the set BF of first Baire category? The answer is we don't know, because this proof is adapted to the case when A is totally disconnected and closed. But in this case, we cannot take the A to be dense, for example, namely Q, because there not exists a continuous function psi that is 0 over a dense set without being 0 everywhere. So we don't know. This approach cannot give any clue to the question 1. The second question is, if I is an interval of finite measure and f is continuous, can be VF having measure equal to b minus a? Here the problem is very similar because the construction by Danjois requests that P is perfect, namely closed without isolated points. And so a closed set totally disconnected of measure equal to b minus a cannot be possible because the complement is open, but the complement has measure would have measure 0. That is clearly absurd. And the third question, deeply related to the other two, can if VF is R, exists a function f that is continuous on a dense set of points? These are questions that our approach is not able to tackle. If someone have an idea, a suggestion, or somehow other ideas, any ideas will be welcome and very welcome. Yeah. To conclude, only to show a small bibliography on which you can find the book by the Coster and Abes that gives the first clue to this problem. The work by Danjois that you can see is a very thought article, big article. Our article on the topological degree of planar maps, and the book by Olds about continuous fraction, that is a very interesting book that gives all the basic property of continuous fraction and basic tool we have used in this work, and it is very, very readable. With this, I have concluded. I thank all of you for follow me, and if there is any question, I'm here. Thank you to everybody.
Thank you, Giuliano, a lot for your seminar. Now, if somebody wants to do a question, he can unmute himself and do a question. Giuliano, sorry, but in all the example that you built, what can you say about the measure of BF? This 0 in all the examples that you construct?
The set VF in what example? For in this example for
no, because you asked yourself question 2 at the end, no? If you can do
namely in the example by Danjois that is made over the interval 0, 1, he constructed the function over a Cantor set or a Smith-Volterra Cantor set, namely a totally disconnected closed set. The measure here can be all the value between 0, that is the case of the standard Cantor set that has 0 measure, to any measure strictly less the measure of the interval. The case in which f is continuous, because if f is not continuous over the entire interval, I have shown that VF can be all the interval, then it has full measure. But if we request that F is continuous over a finite dimensional interval, then VF has to have a measure strictly less than the measure of the interval. With this kind of construction, because we have not proved that it is impossible for a continuous function having VF, having a set VF that has exactly the measure of the interval. We are not able to construct it with these tools, but we have not proved that this is impossible.
Okay, thanks. Okay, so it seems to me that there are no more questions. So I propose to thank Giuliano again for the seminar. And as usual, we meet on next Friday. Thank you.
Thank you to
Thank you
everybody.
all.